Welcome to Texas State University's Chemistry 2330 Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 4, Part 2 of Alkenes and Alkynes. In the last slides, we learned that what the double bond means for alkenes and alkynes. There's a double bond in alkenes and a triple bond in alkynes, and we learned some of their general properties. Today, we're going to learn a little bit more about the nomenclature and how we add to the previous nomenclature rules we have. Okay, using that IUPAC name system, we are going to use the infix ene, En, to show the presence of a carbon-carbon double bond. Remember, for alkene, the E at the end just means we have a hydrocarbon. We can have other things at that end, like an all or a amine, depending on what kind of functional groups we have. So we need to make sure that we're only using that infix, okay? We're gonna look at the number of carbons in the parent chain must contain both carbons of the double bond, and we also will number it from the point where the double bond has the lowest number possible, okay? And we'll practice that in just a minute here. We're going to follow all the other IUPAC names for numbering and naming of substituents. If we have a cycloalkene, the number of atoms in the rings begins with the 2 carbons of the double bond. So the double bond is going to always start 1, 2 in the cycloalkene. Okay, so let's play with a few of these structures just to make sure we have our understanding of these here. And so when we look at this compound right here, we have 1, 2, 3, 4, 5, 6 carbons. So we know we're going to start with a hexa as our prefix, okay? Now, we have a double bond, so we have ene as our infix, and we have the fact that we don't have any other functional groups means an E at the end is going to be for our suffix. So when we look at this, we have to number it such that the first and second carbons of the double bond are at the lowest number. This is easy to do in the alkenes at the end of the chain because we can start at 1 and 2 where the two carbons of the double bond are. So in this case, because the double bond starts at the number 1 carbon, we do not have to specifically say it's the 1-hexene. However, that's the most appropriate way to label this compound. Is 1 because the first carbon is in the 1 position, hex because it has 6 carbon, E because it is a double bond, and an E at the end because it's only a hydrocarbon. Okay, so let's take the next one and add a substituent to it here. We again already have a parent compound here, has 6 carbons. Notice if we used this as our parent chain, that parent chain would only have 5 carbons, and therefore it is not the longest chain. So our longest chain here is 6, and then we have 1 substituent at that number 4 position because we're going to start numbering at the number 1 carbon of the alkene, leveling through the second carbon and then continuing on through the rest of the chain. So that's going to give us a methyl group at the 4 position on the chain, and our hexene is in the 1 position. Okay, so that's going to give our final name to be 4-methyl-1-hexene. Again, E at the end because it's only a hydrocarbon. Okay, so we can build the level of complexity up higher and higher with different substituents, but we have to remember to follow our rules first. So in the next compound here, we have a possibility at naming the chain as much longer than the 5 carbon chain we have named here, because we could go 1, 2, 3, 4, 5, 6 right here. 1, 2, 3, 4, 5, 6, yeah. So, but that would be incorrect because we have to follow the rule that both of the carbons of the double bond have to be in the parent chain. That means we have to label from this side 1, 2, 3, 4, 5. Now, if we labeled from the other side, that would put the first carbon of the alkene at the 4 carbon. So we must label from this side here. And even though it gives us a longer parent chain to not include it, we must include it in our name because the compound is named for the alkene. So it must be included in that. So now we just have to label our substituents. We have an ethyl substituent and we have a methyl substituent. So we have to put the ethyl substituent first because of alphabetization. We put the methyl substituent second because of alphabetization. And now we're going to add our numbers. So we're going to come up with 2-ethyl 3-methyl 1-pentene. Again, 5-carbon chain, penta, pentene. Okay, so now let's label some alkynes. Alkynes are very similar. We have to include both carbons that have the triple bond in it in the parent chain, and we try to put the first carbon at the lowest number possible. Okay, so when we have it at the end, it's very easy. We know we're going to start with our triple bond carbon first is number 1, 2, 3, and then 4. And then when we name this, we of course have to name where our alkyne is and where our substituent is. So our 1 substituent, which is this methyl group, is on our 3-carbon. So we have 3-methyl-1-butene. And again, the E at the end is because it's only a hydrocarbon. Okay, so we can use all these rules together to name even much more complex structures like this last one here. So we have 1, 2, 3, 4, 5, 6, 7, 6, 7, 6, 7. So there's a total of 7 carbons total possible. Okay, and if we number from this side 1, 2, 1, 2, 3, 4, that would put the alkyne at the 4-carbon. Now, if we label from the other side here in red, 1, 2, 3, that puts the alkyne at the 3-carbon, the first carbon and the alkyne at 3. So that means we have to label from this side and give it the 1, 2, 3, 4, 5, 6, 7 that we have here. And so, all right, so we have 1, 2, 3 alkyne, and we have 7, so that's heptane. Okay, and we have 2 substituents, 1, 2, okay, and they're both on the same carbon, the number 6 carbon, okay, so that means we have no other substituents, so methyl would go right here. If we had ethyl, the ethyl would come before methyl, because remember the di doesn't go in with the alphabetization. So now we have 2 methyl groups on the 6, so it's 6, 6 dash dimethyl dash 3, because our first alkyne carbon is on that 3-carbon, heptine, and again the E at the end because it's only a hydrocarbon. Okay, so see, we're just adding to those first few rules of nomenclature, but the key here is in naming alkenes and alkynes is that the double or triple bond must be in the parent chain, and the first carbon in that double bond or triple bond must be the lowest number possible, and then all the other rules apply after that. Okay, so because these are very commonly used in industry, we actually have common names for a lot of these lower molecular materials. Okay, so in the IUPAC name here, when we have this small molecule here, we have 2 carbons, so that would be an ethyl or an eth as our parent, and ene would be our double bond, and the fact that it's only a hydrocarbon, we'd have the E at the end, so it'd be ethene would be the IUPAC name, but it's commonly known in industry as ethylene. Okay, so it's an ethyl, the ethyl group with an ene in it, and so that's pretty common in the engineering names for these chemical compounds. So if we were to have 3 carbons, we would have prop, and then we have the ene with the E at the end, so propene would be the IUPAC name, but it's commonly called propylene because the propyl group is 3 carbons and we have an ene in the compound somewhere. Okay, so if we were to name this compound here, we have a methyl group as a substituent on a 3-carbon chain, so it should be methylpropene. So it'd be 2-methyl-1-propene would be the IUPAC name. However, in industry we call this isobutylene because it's an isomer of a butyl, because there's 4 carbons and it still has an ene in it. So isobutylene. So that would be the common name for that. Okay, so now let's go to alkynes and get a little more specific. It follows the same rules as the alkenes in the fact that the parent chain must contain both of the bonds in the triple bond. We want to number the parent chain so that that double bond has the lowest number possible, and then all the substituent rules follow after that. So when we have a functional group changing the name of a parent, you think of it as it's the one that has to control the numbering system. okay? So now, in the previous slide, we learned that because that double bond, we do not have free rotation. So we can't just rotate that around and say, oh, this is the same compound as this. Because there is no free rotation and it locks those substituents in place, we learned that there was a cis and trans isomerization available to us, okay? So in this case here, we have 1, 2, 3, 4, 5, 6 carbons. So we have a hexene in the 1, 2, 3, 1, 2, 3. So the first carbon in the alkene is going to be at that position. So that's our 3-hexene. And because the two groups are on opposite sides of the double bond, and when I say opposite sides, I'm talking about if we drew a line through this double bond here, are the groups on opposite sides? If they are, that's the trans configuration. And if they're on the same side, this is the cis configuration, okay? So because there's no free rotation, we do have to be properly naming these things without being ambiguous. We must name them that way. Okay, so let's actually name this one here. We have 1, 2, 3, 4, 5, and then if we look at this, this is actually a methyl group here. So we actually have a 5-carbon chain right here. We have 1, 2, 3, 4, 5, 1, 2, 3. So the carbon would over here would be our 3-carbon if we named it from this side, and our 2-carbon from this side. So we number it from this side, so the carbon in the double bond is the lowest number. And now let's look at our substituents. We end up with 1 substituent on a 3-carbon and 1 methyl substituent on the 4-carbon. So, and now our last thing we look at is our cis-trans isomerization. They're both on the same side of this imaginary line through the double bond. Therefore, it's our cis 3-methyl 4-methyl, so that's 3, 4 dimethyl dash 2, because we have to show where that alkene is, pentene, okay? So we're just adding that extra layer of identification on there, okay? The thing that we have to realize here is this only works if we have 2 substituents on our alkene. The other 2 substituents have to be hydrogens to have cis-trans isomerization. What if you have 3 different groups on your alkene? We have to use a different naming system, okay? When we have more than 3 or more groups there, we have to use what we call the EZ configuration, okay? So in EZ, it helps us identify that we have, number 1, 3 or more substituents there, and we give an exact naming structure so that we can't confuse 2 different compounds for the same, okay? So if the highest priority groups are on the same side, that same imaginary line through the double bond here, if they're on the same side, we call that zusammen, or Z, okay? Zusammen means same side. So if you want to remember this, Z is zusammen, and the Z groups are on the same side, okay? So that being said, if we draw that line through there and those 2 higher priority groups are on opposite sides of that imaginary line, that's entgegen, or opposite side. And so we have same side, Z, opposite side, E, okay? All right, so now that we know it's kind of like cis and trans, but we're talking about highest priority, now we have to define what highest priority means, okay? So when we're looking at priority rules, the first thing we look at is basically the atomic number of the substituent we're talking about, okay? When we look here, that's just whatever is directly bonded to this carbon-carbon double bond on one side of the double bond versus the other side of the double bond, okay? So, and when we think about this, if they're on the same side of this imaginary plane here, when we look at EZ, we are going to actually be comparing which group is the highest on this side versus which is the highest on that side. Notice right here. So the highest on this side is on here, and the highest on this side is over here. It's basically we cut the double bond in half to look at whether they're on the same side or opposite sides. But when we're assigning priority, we have to cut it in half vertically to see, to compare the priorities. And I'll show you that again here in a minute. Okay, so our priority rules, first rule is atomic number. It kind of goes with molecular weight, but atomic number is really what we use here. So hydrogen has an atomic number of 1, so it's a lower priority than if we had a methyl group or a CH2 group. So, our hydrogen is typically always our lowest priority group. And then as we move up from carbon to nitrogen to oxygen, sulfur, and to the halides here, those get higher and higher atomic numbers, and therefore they have higher and higher priorities. Meaning if you had this group, this group, this group, and this group all on the same compound here, this would always have the highest priority. Then the next priority would do this, and the next priority, etc. Okay, so we look for the highest priority on that X right here. So we're trying to decide which of these two groups is on the highest priority on that side first. And then we look at which two groups are the highest priority on this side second, okay? And if this group and this group are the highest priority, they're on the same side, they're Z, okay? But if that group and this other group over here is the highest priority based on this midline here, then they're on opposite sides and they become E, okay? So if we have just the, and if we can use just the atomic number to assign priority, great, but it's not always that way. So once we have atomic number assigned, and we have two of the things that have the same atomic number. Let's say we have a CH2 group and a CH3 group over here on either side here. They both have carbon, so they're both assigned as the same priority. Now we have to look at what's bonded to that carbon. So in the case of a methyl group here, the lowest priority would be with a hydrogen bonded to that methyl group, okay? Because hydrogen has the lowest priority in our previous rule. The next would be something like a carbon bonded to it. That would be a higher priority than the hydrogen because the carbon bonded to that carbon is a higher priority. So then nitrogen would be higher because the nitrogen bonded to that carbon is a higher priority than the carbon. And oxygen and chlorine, etc. So we're going to go with the next atom over that usually identifies the priority. Okay, by looking at the first atom and then what's bonded to it, that usually assigns priority. But every once in a while, you have to come up with another rule. And the next rule is if you have something like a double bond, a carbon-carbon double bond, or a carbon-oxygen double bond next to that, we have to count each of the bonds as being bonded to that atom. So if we think about this carbon here is bonded to a carbon, but then the second bond counts as a second carbon, okay? So it counts as a second carbon. So if it's double bonded, you have to count carbon twice, okay? That means if you have a carbonyl here, where you have a carbon double bonded to oxygen, that means that carbon counts as being bonded to two oxygens. Okay, so that being said, the ethylene group is a lower priority than this aldehyde group because oxygens are higher atomic number than carbons. So this group would be the lower priority and this group would be the higher priority. Rarely do we have to move beyond this to identify them correctly, okay? So what we're going to use is these three rules of determining priority, and we're going to identify the E and Z on several alkenes, okay? So what we're going to look at here, and we're going to start with, let's start with the one side. So again, we're looking at what's on, are they on the same side or opposite sides of this line, okay? And so we only have to assign the highest priority on each side of this double bond, right? So we're looking at which of these two groups is highest, and then which of these two groups is highest, and then we're going to look at the two groups that are highest and see whether they're on the same side or the opposite side. Okay, So if we look at this side here, we have a carbon with 3 hydrogens on it, and we have a carbon with a chlorine on it, okay? So the carbons are the same, so we have to go one more atom over, and now we're comparing chlorine to hydrogen. Chlorine is a higher molecular number, a higher atomic number, therefore this is the highest priority, okay? With that being the highest priority, we don't care about that substituent anymore, okay? Because we've identified this one as our highest priority, okay? So on the other side here, we have a carbon bonded to a hydrogen and a carbon bonded to a carbon. Carbon has a higher atomic number than hydrogen, therefore it takes priority, which means that this one doesn't matter anymore. We only are worried about this group here. So this has our highest priority on this side, okay? So if this is our highest priority on this side and this is our highest priority on this side, they are on opposite sides of that double-double bond line, and therefore they are E, because E means engagen on the same side, okay? So let's do the next one and use those same rules. Again, we're going to look at which is highest priority on either side of this line first, okay? And when we look at this side here, we have chlorine right here, which is has an atomic weight of 35, and this has an atomic weight of 80. I forgot the exact atomic numbers, but that makes bromine our highest atomic number, and therefore it has priority on that side of the double bond, okay? On this side here, on the other side, we have this. If it's not written, we understand it to be a hydrogen. Hydrogen is lowest priority, carbon is our highest priority. That means that's our highest priority on this compound. So when we draw our line through the double bond here, we have both groups on the same side of that double bond. Therefore, this is the Z isomer, okay? Let's take that one more and look at some longer chains, okay? Again, the first thing we're gonna look at is what's the highest priority on each side of this double bond. And when we look at that, we see that this has a carbon and this has a carbon with another carbon attached, so that makes this our first priority. Let's do that quickly to their side. We have a carbon, but we have a carbon with 2 carbons on it, so that makes this our highest priority. So now we're going to draw that midline again, right here, and on this midline going in the opposite direction, we have one on this side and one on that side, making them on opposite sides, making it engagin, or opposite side. Okay, so let's do our last one here. Okay, so when I say dividing up, we have to divide them one way first and then the other way second to see which way they are. And we always go across the double bond first to assign priority, and then the two things that are on the same side of the other axis is our E and Z. Okay, so let's look at that one right here and assign priority. Since this is assumed to be a hydrogen, that means this has our first priority. Okay, and here we have a carbon bonded to one carbon and a hydrogen. Here we have a carbon bonded to a carbon and a carbon. 2 carbons outranks a carbon and a hydrogen. Therefore, this gives us our number 1 priority on this side. So if we draw our midline again, we have 1 on this side, 1 on this side, giving us our opposites. They are not on the same side, therefore they are E, and we have our E and Z configuration. Okay, so we're going to take our double bond, we're going to cut it in half. Look at one side first, the next side second. Now, once we've assigned priority, we're going to see are the highest priority on this side on the same side above or below that double bond. If they're both above the double bond or both below the double bond, they're Z. If one's above and one's below, or one's above and one's below, then we have E, okay? So now we can have trans isomerization or easy isomerization in rings. However, because of ring strain and because of the fact that those carbons here, these carbons are sp2 hybridized and have to maintain 120 degrees, you have to get the ring big enough so that you can get to that sp3 hybridization. So that means the smallest ring you can see cis-trans isomerization is actually an 8-membered ring or cyclooctene. Okay, above cyclooctene, you can have cis-trans isomerization. Below that, with cycloheptene, cyclohexene, and cyclopentane, you cannot. Okay, so now what if you have more than one alkene or alkyne in a chain? Okay, well, that means we also have to identify the cis-trans isomerization of those individuals if they only have 2 substituents. And we have to go EZ if there's more than 2 substituents on each of the double bonds, okay? So when we have this, we again want to number it such that the first alkene has the lowest number possible. So in the case of this material here, we actually are numbering it from this end because this would give us a 1, 2. If we numbered from the other end, this would give us a carbon and a 3. So that would be higher than a 2, therefore we can't number it from that side, okay? And so when we do this, we can say, okay, we have this group and this group are on opposite sides, so that's trans. This group and this group are on opposite sides, they're trans. And this carbon, the double bond starts at a 2, and this one, the double bond starts at a 4. So that gives us trans, 2,4, heptadiene, okay? Notice we shove the di right in between the number of carbons and the functional group of the carbons. So we have heptadiene. If we had 3 double bonds in there, we'd say heptatriene. And so we shove that, you know, that modifier, that number modifier in between the number of carbons and the functional group, okay? So let's look at the other isomer possible from the same compound here. We're going to, again, number the same way. The 2 carbon here, these are on opposite sides, so that gives us trans. But notice that these 2 are on the same side, giving us the cis configuration. So, well, this is the trans 2,4-heptadiene. This is the trans cis 2,4-heptadiene, okay? That may look like a small difference. They have the same number of carbons, they have the same number of double bonds, but because they're different isomers, they do have different properties. And because there's no free rotation around that double bond, okay? So we do see differentiation between these things. And now, using all these numbering systems, naming systems, we can differentiate disubstituted alkenes, disubstituted dienes, multi-substituted alkenes, and alkynes.